Okay, so we're looking at Riemann Sums, section 5.4. Again, this is one of the toughest sections, so y'all please be sure that you listen, rewind, whatever you need to do to make sure that you've got this down. Please write down any questions and let me know tomorrow. Riemann Sums and the definition of definite integral, day 2. Our objective is to use Riemann Sums and limits to define and estimate values of definite integrals. So we're going to start with where we were yesterday and then move forward in a hurry from there. Okay, these are helpful formulas. If you remember, we did these last year, summation formulas. If all you have is a constant, then this is your formula, where n is going to be your upper bound and c is the constant times that n value. If you have just from I equals 1 to n of I, number 2, then you want to use the formula n times n plus 1 over 2. If you have I squared, then that's your n times n plus 1 times 2n plus 1 over 6. And if you have I cubed, then that's your n squared times n plus 1 squared over 4. So make sure that you've got these formulas down. As we go through and use these, we're going to be looking at all of our Riemann sums having exactly the same widths on these, so that's going to make these formulas very useful. Again, over on the left, be sure that you've got this piece right here, your Riemann sum. From I equals 1 to n, f at c sub, you could do c sub k or c sub I times delta x sub k, and you want to be sure that you know this piece right in through here, that your area is the same thing as your limit, and that's the same thing as your definite integral. So we're going to be using those things over and over again, so let's get going. Okay. Quick example just to remind you how to use your formulas. It says evaluate for n equals 10, equals 100, n equals 1,000, and as n goes to infinity. And we may not do all of those, but let me at least show you how to do it with the 10. If you remember correctly on these, what we want to do is pull the n squared out to the front. Okay, and then you do your sum from I equals 1 to n. And what you're left with is that I plus 1. Well, remember, those things can split. To where you can rewrite it like that. That's the exact same thing as what's up above there. And then use your formulas. 1 over n squared, your sum from 1 to n of just plain old I. That was the reason that we wrote those formulas down before. If you've got a plain old I, then that's what you want to look at. So n times n plus 1 all over 2 plus this second one right here. It's always the constant times n, but your constant's a 1, so it's just an n. Okay. So simplifying just a little bit here, you've got 1 over n squared, and that's going to be n squared plus n. And I'm going to go ahead and get a common denominator here in order to put that all over. And that would simplify to n squared plus 3n, which we will write in just a minute. So at the moment, all of these things equal what we had up there. But now then, the reason this is so nice and those formulas are so handy is because I can go back and I can plug in anything I want. If I want to do n equals 10, then what I do is 1 over 10 squared times the n squared is 10 squared plus 3n. Well, 3n is going to be 3 times 10 all over 2. Okay, so there's your 1 over n squared, and n squared plus 3n all over 2. You've got what? 130 over 2 is 65 over 100, and that would reduce to 13 over 20, I believe. So there's your sum, not a problem. If you want n equals 100, you just plug 100 in everywhere that we plugged in 10. Okay, I want to be sure, though, that we do get the n goes to infinity. And that one's an important one. So if I want my limit as n goes to infinity of my sum down there, the 1 over n squared times n squared plus 3n all over 2. And then what I'm going to do, I'm going to distribute that n squared through. So limit as n goes to infinity of n squared. When I run that through, that's going to give me n squared over 2n squared plus 3n over 2n squared. Okay? Well, the n squareds are going to cancel right there, and I'm left with 1/2. And then right here, this n will cancel with one of those, but as n goes to infinity, 3 over 2n is going to get infinitely closer to 0, because that n is going to get humongous. So I'm basically left with 1/2 right here. Okay? If I had plugged in the 100 and the 1000, you would have seen those getting closer and closer to 1/2. Where at 10, I had 13 over 20. Then when I plugged in 100, I'd have had a little bit closer, and I plugged in 1000, I'd have had a little bit closer, and then as n goes to infinity, I get 1/2. So it would have gotten closer and closer to that value. Okay. Riemann sum reminders real quickly. Those were your summation formula reminders that we just did, our Riemann sum reminders. Each subinterval has this width right here, b minus a over n. Be sure that you have that. Okay, we're going to symbolize that as delta x. The endpoints of the interval, we talked about this yesterday. Okay, we said these are like our c sub I values. That's c at 0. These are x values that we're going to plug in to our f at c sub I. This right here would be c at 1. This right here would be c at 2. These are all going to be little x values going across like this, and we're going to plug those into our function in order to find out what the y value is. Okay, then we'll multiply and have the area of our rectangles. Again, this is just a reminder. These are lower sums here on the left, right here. These are your lower sums because everything is below the curve. These are your upper sums right here because everything, all your rectangles that you drew were above the curve. And so therefore you know that your actual area has to be somewhere in the middle. Somewhere between those two numbers. And this is that thing that we looked at yesterday. We said that in-between area can be represented exactly as a definite integral. That doesn't mean a lot to you yet, but it will. Okay? All right. So we're supposed to find the area of the region bounded by the graph of f of x equals x cubed, the x-axis, and the vertical lines x equals 0 and x equals 1. Let's first draw our graph. Looks like that right there. There's our x cubed, and I want to go from 0 to 1, so that's going to be from right here over here to 1. And that tells me I am going to find that area right there, that little bit of a shaded area right there. Okay. A couple of things that we want to be sure that we do on this. We want to notice that f of x is x cubed. That's a big deal because I'm going to need to do f at c sub I, and my c sub I is going to go right in right that spot. Well, if I'm going to do that, then I need to know what c sub I is. C sub I is always a plus I delta x. Okay. Now that I value is just telling me what little rectangle I'm moving over to. 0 rectangle, first rectangle, second rectangle, that type of thing. Okay, I have 0 widths, 1 width, 2 widths, etc. Okay, we talked about that yesterday. Our a value is 0 because we got this right here. It says x equals 0, so my a value is 0 plus I is going to change from one thing to the next every time I move over another width. But I've got to multiply times delta x, and I don't know delta x yet. So let's drop back down here and find delta x. Delta x is b minus a over n. Our b came from this right here. That's 1 minus our a value of 0. Over, and in this case n, because it didn't tell us how many rectangles, so our b minus a over n is just going to be 1 over n. Okay, so going back up here and plugging that in, it's a plus I delta x, so that's 0 plus I times 1 over n. So that means my C sub I formula is I over N. Okay? All right, so now then, remember we are trying to use this right here. So I'm going to rewrite this as the limit as n goes to infinity of the sum from I equals 1 to n of f at C sub I, which we found to be I over n, times delta x, got to have a delta x out here, so times 1 over n. Okay, now then the f at I over n, I got to come back and plug that into my function that's right here. So this becomes limit as n goes to infinity of, and I'm going to pull, I won't either. I don't want to confuse you yet. Let me plug it in first. I equals 1 to infinity to n of, and instead of f at I sub n, I'm going to plug it in now. So that gives me I cubed over n cubed times 1 over n. Now I'm going to pull out. I want my limit as n goes to infinity, and I have a total of 4 n's in the denominator. So I'm going to pull out 1 over n to the 4th to the front and do my sum from I equals 1 to n of I cubed. Now then, that's really nice because we have a formula for that. Okay, that's going to equal, and I'm going to move up here, equals limit as n goes to infinity of 1 over n to the 4th times n squared times n plus 1 squared all over 4. Okay, if you don't remember that, always be sure that you go back, look at your formulas. Okay, and right here on your I cubed formula, you had n squared, n plus 1 squared all over 4. Okay, so going through simplifying my n plus 1 squared, if you FOIL that out, it's going to give you, and I'm just going to jot this in right here in case you need to see it, equals n squared plus 2n plus 1. If not, that's fine because we're just fixing to distribute through. So my limit as n goes to infinity. I'm going to make this one big fraction here with 4n to the 4th in the denominator. In the numerator, distribute your n squared through that n plus 1 squared FOILed out. So that gives me n to the 4th plus 2n cubed plus n squared. Okay, if I split that apart, I have the limit as n goes to infinity of n to the 4th over 4n to the 4th plus 2n cubed over 4n to the 4th plus n squared over 4n to the 4th. Okay? When you look at that, it's pretty obvious to see on these last two terms that your exponent in the denominator is bigger, and so as n is going to infinity, both of these last terms are going to be going to 0. And so you're left with just this first one. The n to the 4ths cancel out and leave you with a 1 on the top. And so your exact area for that is 1/4. Okay, there's 1/4 of a square shaded in on that right there. So that's what we've just found is the area underneath that curve that we had shaded on our cubic function. Okay. All right, let's try another one. Oh, I had extra space there in case I needed it. Find the area of the region bounded by the graph of f of x equals 4 minus x squared, the x-axis, and the vertical lines x equals 1 and x equals 2. Okay, always start with a graph. 4 minus x squared is a parabola that's been turned upside down with a vertex at 4. Since I'm only going from 1 to 2, I'm just going to look at this piece that's in the first quadrant right here. So up here, if I'm at 4, and right here, if I am at 2, that's where the parabola would cross and come down. Okay, and so I am looking at this area right in here. Okay, from 1 to 2. All right, again, always start by writing those central things down. Write down your f of x, write down your c sub I, write down your delta x. F of x is 4 minus x squared. C sub I, that is always your a value, where you're starting. In this case, you are starting at 1. Plus I times delta x. I don't know delta x until I go down and find it. Delta x equals, b value is 2, so 2 minus 1 over n. So again, my delta x happens to be 1 over n. It is not that way all the time, but it's nice when it is. Okay? So c sub I is 1 plus, if you simplify that, I over n. Using our formula, okay, our area is going to equal the limit as n goes to infinity of the sum from I equals 1 to n of f at c sub I. Well, c sub I is 1 plus I over n times delta x, which is 1 over n. Okay, so we're always using those, plugging those in. Make sure we understand that. This time it's a little more challenging because I have this 1 plus I over n that is my c sub I, and it's going to have to go in place of my x values. Okay, so a little bit more work than what the last one was, or the limit. As n goes to infinity, its sum from I equals 1 to n of, and in this case, that would be 4 minus 1 plus I over n squared, because that's 4 minus x squared times delta x, 1 over n. Okay, this is where this gets a little bit complicated. We've got limit as n goes to infinity of the sum from I equals 1 to n of 4 minus, and if I square that out, first is 1, outside and inside, that's going to give me 2i over n, but with the negative distributed through, minus 2i over n, and then your last is plus I squared over n squared, but with the negative comes minus I squared over n squared times the 1 over n. Okay, so kind of working through this a little bit and simplifying what we can. We've got a limit as n goes to infinity. I'm going to pull my 1 over n out to the front. Okay, times. Okay, I'm going to split these things up as I go through. I've got my sum from I equals 1 to n of 3. 4 minus 1 gives you 3. Minus, I'm going to pull the n out in front here, or I guess the 2 over n, and the sum from I equals 1 to n of I, minus 1 over n squared times the sum from I equals 1 to n of I squared. Bigger bracket, sorry, since that was what I started with. Okay, the 1 over n at the end, remember I pulled all the way out to the front. Okay, let me see if I gave myself an extra page on this one. Nope. Okay, so let me add a page and make this thing doubled so that you can see. All right, so that's going to be limit as n goes to infinity of 1 over n times, my first one should end up giving me a 3n minus 2 over n times, your plain old I is n times n plus 1 all over 2 minus 1 over n squared times, and your I squared one is n times n plus 1 times 2n plus 1 all over 6. And I think that will do that. Okay, and so then simplifying that right there, limit as n goes to infinity of, when I distribute the 1 over n through, right here I've got 3n over n minus, this is going to give me 2n squared plus 2n over 2n squared, because this n right here and this n right here give me the n squared in the denominator. Okay, so minus that whole thing right there, minus on this next one, oh yeah. Okay, so this is going to be n squared plus n, and we FOIL that out on the top to where we have 2n cubed. First, outside is n squared, inside is 2n squared, and the last is plus n all over 6n cubed, because of the n squared right here with, again, this n from the beginning. That's what gives me the n cubed in the bottom. All right, so kind of reducing and simplifying things. I can tell that from the first one, those n's are going to cancel, and I'm going to get a 3. On the next one, the second fraction is going to go to 0. The first one should give me a 1. Okay, and then on the last one, I should end up with a minus 1/3. Okay, everything else should end up going to 0. If you've got a question on it, ask me tomorrow at school, but I'm trying to get this finished up in a hurry for you. So you have 2 minus 1/3, so it looks like 1 and 2/3 for your solution. So hopefully that's what y'all got. Double check me, please catch me if that's not right. And we've got a couple more things that we'll look at tomorrow, but I just wanted to make sure that y'all were good. We will just finish that same Riemann Sums and trapezoid worksheet. There's not an additional assignment, but we will work on this page right here to make sure we understand. Talk to y'all tomorrow. Bye.